If we want to understand how the clouds impact the climate, we talk about the climate forcing. How do the clouds force the climate? And there are two ways. The first way is through the shortwave radiation, which is mainly the radiation coming from the sun. The second one is through the long-wave radiation, which is the radiation leaving the Earth and trying to get out to space to cool the planet. So let's first talk about the shortwave radiation, the incoming radiation. What we've already spoken about is that clouds, because they're white in color, they reflect a lot of the sunlight out to space. This affects the albedo of the planet. And so generally, clouds will reduce the amount of energy coming into the surface. But this varies by the type of cloud. Also, most clouds don't absorb a lot of energy. They either let it go through the cloud or they reflect it back to space. So we can see here that if we look at the low and the middle and the high clouds, if we look at the albedo, the low clouds reflect about 69% of the sunlight hitting those clouds. Middle clouds reflect maybe 48%. High clouds only about 21%. And the cumuliform, the deep thunderstorms, the cumulonimbus clouds, about 70% gets reflected. So the higher we go up, the high clouds actually reflect less light than the low clouds. And if we look at how much gets absorbed by these clouds, we can see that only about 6% for the low clouds, 4%, 1% for the high clouds, even up to only 10% for the very deep thunderstorms. So clouds don't absorb a lot. They either transmit the sunlight through it or it gets reflected out to space. And this we call the cloud albedo forcing. According to the albedo of the cloud, how does this force the climate? Now we can look here at an example of the reflection, the transmission, and the absorption of energy from the sunlight as a function of the thickness of the cloud, the actual physical thickness starting at around 10 meters, 20 meters, and going up to 10 kilometers, 10,000 meters. And what we see is that as the clouds get physically thicker, we get a large increase in the reflection of the sunlight, and eventually it reaches some kind of saturation. About 90% of the sunlight gets reflected back out. Opposite to this is the transmission. The more that gets reflected, the less goes through the cloud. So the transmission, shown in the blue curve, starts out fairly high when we have very thin clouds, but as the clouds get thicker and thicker, we can see that we have less and less light going through the clouds, and by, say, 1 kilometer thickness, we don't have any light which actually makes it all the way through the cloud. This is one of the reasons when you're standing underneath, say, a thunderstorm or a big, thick cloud, it looks like it's black underneath or very dark color. It's not because the cloud is black or gray in color, it's just that the light doesn't make it through from the top to the bottom of the cloud. But when we look at the absorption, how much light is actually absorbed by the droplets in the cloud, we can see that even when we get to very thick clouds, we're still less than 10% of the radiation which actually gets absorbed by the cloud. So clouds don't absorb much. They reflect a lot, they transmit a lot if they're thin clouds, but it's mainly the effect of the reflection that when we get to thick clouds, they reflect, have large albedos, and this has a cooling on the surface temperatures. If we look at a function of latitude, so this plot shows from the South Pole, 90 south to the North Pole, and this is for a specific day. This is the June solstice, so the 21st of June, which is when the sun is in the northern part of the planet, where we're having most of the radiation in the north, and we have 24 hours of sunlight at the North Pole and 0 sunlight at the South Pole. We can see here the difference in the energy, the radiation coming into the Earth at the surface, shown in red, and at the top of the atmosphere, shown in blue. And again, this shows that normally we would expect at 23 degrees north, we would have the maximum, but this is looking over the whole day. So at the North Pole, if you have 24 hours of sunlight, you actually have a similar amount of sunlight than you would have, say, in the tropics, where you have day and night together. But when we include the clouds, you can see we have less. The red curve is a lot lower than the blue curve, and the main effect here is clouds. Clouds are reflecting the sunlight back to space, and so we have a lot less radiation making it to the surface to warm the climate. Now let's have a look at the long wave, the effect of the long wave, what we call the cloud greenhouse forcing. The yellow arrows show the heat which is given off by the Earth, and previously we spoke this. The amount of heat given off by the surface depends only on the temperature and the temperature to the fourth power. So it's a very nonlinear relationship, very strong relationship. A small increase in temperature, we have a big increase in the radiation emitted, which is basically these yellow arrows. If we have clouds in the atmosphere, this gets absorbed by the clouds. Some of it will be re-emitted down, and some of it will be re-emitted up, shown by the red arrows. But without the clouds, all of this would go out to space. And so basically, if we just look at the effect of the long wave effect, what we call the greenhouse forcing of the clouds, clouds tend to warm the climate because they're trapping in some of this heat. So we have basically two opposing forces. We have the albedo effect, which is reflecting sunlight, cooling the planet, and we have the cloud greenhouse forcing effect, which is warming the climate. And we can see this in these two plots for a single month. This is March 2000. Looking from satellites from space, the top plot shows how much of the shortwave is reflected back to space. And the color bar shows you the shortwave flux. So this is looking down at the Earth and seeing how much sunlight comes back to the satellite, measured in watts per square meter, ranging from 0 up to 210. Where we have white areas, light areas, we have a lot of reflection and the sunlight leaving and actually not making it to the surface if we have clouds. And we can look at, say, South America, Africa, Indonesia, these areas where we see the white colors. This is because of clouds. The clouds, normally we have, say, rainforests at the surface, which are very dark in color, would absorb that energy. But because we have clouds and thunderstorms there all the time, they're reflecting the sunlight back to space and actually having a cooling effect. We see other areas, the dark areas, over the oceans mainly, where we can see that we're having very little reflection because here we have the oceans with very little cloud cover and they're very dark. The color of the ocean is dark, so the sunlight is being absorbed at the surface. And we have other areas like the Sahara Desert, which don't have clouds, but they're also very bright in color, so they reflect the sunlight. So it's not always easy to differentiate between bright surface like snow and ice and deserts and clouds, which also reflect the sunlight. In the bottom plot, if we look at now what's happening with the long wave radiation being emitted from the Earth, and looking down from a satellite, we can see how much makes it to the satellite and how much doesn't make it and gets absorbed on the way up. And again, we can see that around South America, Africa, Indonesia, we can see we actually have a minimum. The blues are less energy is leaving than in the reds. The reds we see a lot, and the reds and yellow, a lot more energy is leaving because we have no clouds and it's warm there. But if we have warm temperatures and we have clouds above it, like we have over the Amazon and over Africa and over Indonesia, then the clouds act like a blanket and they trap in this long wave radiation. So we can see that on the top plot, the clouds in the tropics are actually cooling the planet. They're reflecting it back to space. In the bottom one, they're trapping in the heat and actually warming the climate. So both effects are occurring, both a cooling and a warming. And here, if we just take a snapshot of one day, you can also see this effect. This is for 22nd of June, 2002. Looking here over the US, you can see here, again, where we have the clouds, the shortwave reflection, the whiter the region in the top plot, the more reflection and the loss of energy, a cooling effect. But if we look at the bottom one, where we have the blues, we also have less energy leaving, more trapping in of the long wave radiation, a warming effect. So the clouds can have both a cooling and a warming effect.